Welcome everyone to 2.3. In this section we're going to learn all about these things, differentiation formulas. And the claim is, right, in 2.1 and in 2.2 we had to use this thing, the limit definition of the derivative, and this took a lot of time. It can be quite difficult, and while it is very important that you don't forget this, right, this is a major learning objective for this course, and lots of Calc 1 courses out there. But there are some ways to do these things faster, and that's what 2.3 is all about. All right, so in this first video here, I'm going to give you a constant and a linear differentiation rules. We're going to get the power rule and see how powerful it is. And then, of course, we're going to try to apply these things to take derivatives very, very quickly. All right, so starting off then, the theorem 3.1, suppose that f of x is equal to some constant function, right? So let me go ahead and draw this here. So we have f of x is some constant function. It doesn't matter how tall it is, but we know for constant functions, we have a nice horizontal line. So it doesn't matter any c value here, and it can be 2, 5, a million, it can be negative 30, right? Positives, negatives, anything like this, any constant function. Then the derivative of this function here is going to be, well, remember, derivative is the same thing as slope, right? Slope at a point. And so if you go along any of these points here, and I ask you, what is the slope of this function at any of these points? Well, at each one of these points, the slope is 0, right? It's a nice horizontal line. So therefore, the derivative will be equal to 0. So if we just remember that derivative, right, is slope at a point, then we can get the answer to this. Likewise, if we have f of x is equal to some linear function, mx plus b, so right, this is going to look something like this, some linear function. And of course we have, this would be height b, and we have a certain slope m. Then again, as you go along any of these points here, and I ask you, what is the derivative at all of these points? aka, what is the slope at all of these points? Well, it's always the same thing, right? The slope is m. That's the whole deal with linear functions. So therefore we have the slope is m. All right, let's get some practice applying these rules then. So first one, if f of x is equal to the constant function 7, right, our goal is to find the derivative. So we're going to have f prime of x is equal to 0, thanks to this rule up here. For part b, right, take the derivative. So I'm going to have g prime, now we have t variables. Well, we have, this is our constant, right? So this is the y-intercept, and our slope here is negative 2. So therefore the slope, right, the derivative of this function will be negative 2. Again, it doesn't really matter what the t value is or what the x value is up here, right? For all of them, the slope is negative 2, and likewise for all of the x values, the slope is 0 in this case. Here's one that's a little bit more difficult, right? Sometimes you have functions that look complicated, but actually we can simplify these things down. So in this case, if we first do a little bit of algebra, this top function, this numerator function up here, can actually be factored, right? It's actually a difference of squares problem. So if I do this, it can be 2x minus 1 times 2x plus 1. Go ahead and FOIL this all out and make sure that you get back to where you started. All this divided by 2x plus 1. And so you can see there's some nice cancellation that happens here. And so in reality, this actually is essentially a linear function. Maybe not at one specific point. You don't want to divide by 0, but most of the time it is a linear function. So now the question is, what is the derivative? Well, this function behaves like 2x minus 1 most of the time, so its derivative is going to be equal to 2, the slope. All right, so that's taking some derivatives of some constants and linear functions. Let's do something a little bit more complicated. So yes, we get something called here the power rule, which is indeed very powerful. Before I give it to you though, got to go over a little bit of algebra, right? So if I have n is any real number, then sometimes we have 1 over x to the n. This can be 1 over x squared, or 1 over x cubed, or 1 over just x to the first, right? And it's useful to know that this can be rewritten as x to the negative n power. So instead of having x to the positive n in the denominator, you can kind of bring it up to the numerator, so long as you make that exponent negative. We'll see this in action here in just a second. Likewise, if you have the nth root, right, so square roots, cube roots, fourth roots, all these sorts of things, any nth root, you can rewrite this as x to the 1 over n power. And of course, this applies, both of these apply so long as they're defined, right? So you don't want to take square roots of negative numbers, you don't want to divide by 0. So wherever this is defined, you can make these trades. Okay, so the power rule says if you have a function which is a power of x, x squared, x cubed, x to the fourth, x to the 1,000,000th power, whatever, right, for some real number n, then the derivative is equal to, and very interestingly enough, it's the power comes down, and then you multiply by x to the, and you reduce your power by 1, so n minus 1. All right, so let's go ahead and see this in action here with an example. So in this first case, we want to take the derivatives of all of these things. We have x cubed. So the way that we would use the power rule here is, well, now our n is 3. So the 3 would come down, and you get times x to the 3 minus 1. So this would be x squared. So it's 3 times x squared is the derivative of this. Now this is a rule, right? I haven't proven this. This is a theorem, right? There is a very complicated proof. It's a difficult proof here in order to show this, that this is actually a mathematical theorem. But notice this is way, way, way faster, right, than that limit definition of the derivative. The claim is if you use the limit definition of the derivative, you can show the same thing. It's just it'll take you, 10 or 20 minutes, and we just did it, like that. All right, let's go ahead and apply this to a few more things. We have f of x is x to the 0.2. So I want to know, again, its derivative. Well, in this case, our n value is 0.2. So applying the power rule, the 0.2 comes down, and we have x raised to the, and I need to reduce my power by 1. So I need 0.2, subtract away 1. So that's going to be negative 0.8. Okay, another one. G of x. So I'm going to go ahead and take its derivative. Here we have x to the 5/2 power. So the 5/2 is going to come down, and we have multiplication by x, and we reduce our power by 1. So we go from 5/2 to 3/2, right? Because 1 is the same thing as 2/2. All right, now I told you these important definitions up here. Let's go ahead and use those. So part D here, I have 1 over x. Notice this does not look like, when I have it written like this, it doesn't look like x to any particular power. But if I remember back up here, that I can go ahead and rewrite things that look like 1 over x to some power as x to the negative that power, right? Then we can go ahead and rewrite this, because this is 1 over x to the first power. So before I even take the derivative, let's go ahead and rewrite this. Applying that definition, we would have x to the negative first power. So now I have it looking like something that I can apply the power rule to. So let's go ahead and take the derivative. And now our n value is -1, so that -1 will come down, and then I multiply by x raised to the, well, I need to reduce my power by 1. So it goes from -1, when I subtract away another 1, then I'm going to get -2. All right, something a little bit more complicated here. I have 1 over x cubed. Again, the first step is going to be rewrite this. So this is going to be x to the negative 3rd power. I'm going to bring this up into the numerator using this first rule right here. Now let's go ahead and take the derivative. So capital F prime of x is equal to the -3 will come down. And then I have x to the negative 4th power, right? I reduce my power by 1. Square root of x. Square root of x. Well, now we're in this case, right? So square root is the same thing as the 2th root, right? Or the 2nd root. So in this case, the square root is the same thing as x to the 1/2 power. So again, I'm going to go ahead and rewrite this first thing, x to the 1/2 power. And now I can go ahead and take the derivative of this. The 1/2 is going to come down, and then I reduce my power by 1. So 1/2 subtract away 1, I'm going to get -1/2. And then finally, the cube root. So the cube root of x, well, that's going to be the same thing as x to the 1/3 power. Again, using this definition right here. So the cube root. So take the derivative, and the 1/3 comes down, and I get x. Let's subtract 1 now, so 1/3 minus 1, that's going to be negative 2/3. And there we go. So we've actually taken a lot of derivatives very, very quickly. Still, though, the claim is these are pretty simple functions, right? So we want to start combining these things with more functions, right? So let's start adding them together, subtracting them, multiplying, dividing, right? So our next video here, we're going to talk about sums, differences, and constant multiples. I'll see you then.